Hey friends, welcome to this channel, and in today's video we'll be discussing about the titration curve of amino acids. So each of the amino acids have their characteristic titration curve. Okay, so now what is titration? Titration is basically the gradual addition and removal of protons or H+. Now today we'll be discussing about the simplest amino acid, glycine. This is the simplest amino acid because it contains H as their R group. So let me first draw the titration curve. This is a quite familiar curve for all of you. And this is the titration line. Okay, let me draw it a bit. Yes, this is the titration line. Now there are 3 points which are important. Let's say this is the first point, this is the second point, and this is the third point. This is pH 0 to 30 and this is a OH negative equivalence. Let's say this is 0.5, 1, 1.5 and 2. Okay, so we are discussing about glycine today. This is the normal structure of glycine, we all know, right? So this is 1, 2 and 3. So the first point, pH is quite low, so H+ ion concentration is quite high, and in this situation glycine will remain as NH3+, CH2 and COOH. There is an error, this CO negative should be COOH, please forgive me. So this NH3+ has one positive charge. Now pH is increasing gradually. So at this stage, when pH is equal to 2.34, NH, this is the so from COH, H+ will start removing, and in this particular 2.34 pH, the concentration of NH3 plus CH2COH and NH3 plus CH2CO negative will be in equimolar state. And due to this equimolar state, previously there was one positive charge and now there will be 0.5 positive charge due to this equimolar state, right? This is the pKa of carboxyl group, that is pK1. This is 2.34 for glycine. Now we'll be discussing about point 2. pH is again increasing gradually and it reaches to 5.97. In this state, this is called the isoelectric point or Pi for glycine. Okay, in this state the first proton removal is complete and the second proton removal has just begun or just started. Okay, and most of the glycine will remain in this state NH3 plus, CH2 and CO negative. So the first removal has completed from COOH and the second removal is just started. So this will be the form, and as a result you can see that there is one positive charge and one negative charge. We can say that this second proton removal is going to start. So there is one positive charge, one negative charge, so the total charge will be 0. This is the most stable point. So this is Pi and that is 5.97. Now we'll discuss about the point 3. So pH is again increasing gradually and it reaches to 9.6. In this state pH is quite high and H+ ion concentration is quite low. So one proton from this NH3 plus will start remove. So there will be NH2, CH2, COO negative. So there is no charge on amino group but one negative charge on carboxyl group. So the total charge will be 1 negative. There is 0.5 positive charge and in this case there will be positive. So at very low pH there will be one positive and very high pH there will be one negative. So for glycine, pK1 is 2.34, but for other acids, let's say for aspartic acid or acetic acid, not aspartic acid, pK1 is kind of 4.76 or 4.7. Now why this decrease for glycine? That's because of a repulsive force between the departing proton and the amino group present on alpha carbon. If we look at the amino acid structure, we have the alpha carbon, NH3 plus and CO negative. So from COH, 1H plus is going out, and there is a repulsive force between the NH3 plus and H plus. So due to this repulsive force, this pK1 is quite low than other hydrocarbon and other acids, organic, inorganic acids. For pK2, glycine has the pK2 of 9.60, but for aliphatic amines, pK2 is more than 9.60. Okay, we can say that this pK2 is more than 9.60. Why? This is because this is the normal structure of amino acid, and this COO minus group tends to attract H plus from NH3 group, okay, from amino group. So there is an attractive force or attraction, and due to this attraction, very easily one proton from NH3 plus is removed, and as a result there is low pK2 for glycine and other amino acid rather than other aliphatic amines. So the repulsive force works on pKa of carboxyl group, and attractive force works on pKa of amino group. Okay, remember this thing. Now when if we draw like this, that pH low to high, we have pK1, then pi, and then pK2, right? So sometimes question comes that calculate the pi. They give pK1 value, pK2 value, and sometimes pK3 value, and then they ask us to calculate pi. So we'll discuss about three kinds of amino acid. One is glycine, where R is H group. Another one is aspartic acid, where R is the acidic group, and lysine, where R is the amino group or basic group, right? For glycine, the simplest one, pK1 for carboxyl group is 2.4, let's say. pK2 for amino group is 9.8. So pi will be half of pK1 and pK2. Okay, we are not considering pK3 because we know our group is hydrogen, so the pi will be 5.97. For aspartic acid, pK1 for carboxyl group, this is the pK, and pK3 should be of R group. So pK1 for carboxyl group is around 2.1. You can get it from any biochemistry book. pK2 is 9.8 and pK3 for 3.9. So this is aspartic acid, so we'll consider both the carboxylic group or acidic group. So we'll consider pK1 and pK3. So pi will be half of pK1 and pK3, and if we calculate, the value comes around 3. For glycine, pK1 is 2.18, pK2 is 8.9, and pK3 is for 10.5. So lysine, being a basic amino acid, will consider both the amino groups, so pK2 and pK3. So pi will be half of pK2 and pK3, so the value comes around 9.7. So by this method we can calculate the pi value, and also we calculate which amino acid have charge in which pH. So hope that makes sense. Thank you.